Hey guys, welcome back. So today I want to talk about random variables, their distributions, and go through a couple of very common named distributions. There are many, many more than 3 named distributions, but these 3 are super important in biostatistics, super important in medicine, very common for data analysis out there. So the first definition is up on the board. A random variable, talked about variables before, is a measured quantity whose outcome is unknown. So some of the definitions that you see out there say it's a measured quantity with a random outcome. I don't want you to think about an outcome being random as something that resembles a coin flip, something that doesn't have a pattern to it. That is not what I'm talking about. Plenty of variables have a very systematic pattern. A coin flip just so happens to be one where one thing happens half the time and the other thing happens half the time. If you read something out there with that definition, there's a very specific way I worded this. Measured quantity whose outcome is unknown. All right, a bit of notation. Our generic random variable is going to be like a capital X, or in theory, it could be like a capital Y. Something like that. This variable taking on a specific value. Yeah, so this is generic variable. And then this notation is our variable taking on a specific value, X or Y. You see, this is capital and this is lowercase, and when I write, I will try to make it squiggly. I will do my best to remember to make it squiggly, but I think I almost always make a value of variable X, a value of variable Y, lowercase. That's how you can tell the difference. This is the notation throughout statistics. And then, of course, we can look at things like probability of a random variable taking on some specific value, or probability of a random variable being greater than a specific value. Random variable being less than or equal to a specific value. So we have a generic random variable, some values of that random variable, specific values of that random variable, and then we can take probabilities that our variable X takes on some value, bigger than, less than or equal to, not, conditional on. All of those concepts apply, and we're going to see how they apply in our new named distribution world. So, variables have distributions. Variables, I'll use a different verb. Variables follow distributions. And I'll say some distributions are named. They are named binomial, Poisson, normal. And these are distributions assigned to variables, or variables follow these distributions. When we say that, I want you to know that this is imposing a systematic pattern. On the values of our variable X. If I say X follows a binomial distribution, or honestly any other named distribution, I am imposing a statistical model as to what values are going to be common, which values are going to be uncommon, and what values are going to be impossible. When I'm saying that my variable follows a normal distribution, for example, I'm saying that decimals, right? It's like I'm claiming my variable is quantitative continuous. The other two, I'm claiming that my variable is not quantitative continuous. And as we will shortly see, by saying my variable has a binomial distribution, I will be imposing a set of bounds on my variable that it will be defined between 0 and some number. So no negative numbers, and there will be an upper bound. So when you see someone writing something, or me saying, suppose a variable follows a certain distribution, that statement alone imposes a statistical model, right? We're in a statistical modeling class. And this is inherently theoretical. As all models are wrong, some are useful. This exercise is inherently theoretical, but, big but, many cases are known and have been validated. So question everything. But know that there are some cases that are uncontroversial, but you are allowed to question when someone says, hey, I have this variable and it follows a named binomial distribution. You're allowed to say, how do you know? You're allowed to say, what are the assumptions that we're making when we make that statement? Is there any way to verify these assumptions? And sometimes the answer is going to be no. Sometimes the answer is going to be yes. So we're going to start to make these assumptions. And I want you to know that this is an implicit assumption that is made, even if it's not explicitly stated. All right, let's get started. The first named distribution is called the binomial distribution. For the binomial distribution, I want you to think that you're modeling successes in quotations, because they can be very much failures. For example, death, unless you are an exterminator, death is very much not a success. Think successes out of some n trials. This is a distribution to model the number of, count of, successes out of some n number of trials. When we impose a binomial distribution, we write the following. We say our generic variable x, this tilde is read as distributed as, I can change colors to spruce this up a little bit. Read this as distributed as binomial, bin is binomial. And then what goes in here are called parameters. So these parameters are numbers that change the shape of the distribution. They change the mean of the distribution. They change the standard deviation of the distribution. They change the median of the distribution. They change which values of my variable are more or less common. And I'll show you an example in just a second. So the parameters are n, right? That's the number of trials, n, and p. P is the probability of a quote-unquote success on each trial. So when we say a variable has a binomial distribution, we can write it just like this. Our variable x, or capital Y, or capital Z, or capital C has a binomial distribution. And here are the two parameters of that binomial distribution: the total number of trials and the probability of success on each trial. The key assumptions probability does not vary by trial, and the trials are independent. The outcome of the fifth trial does not depend on the outcome of the fourth trial, or the third, or the second, or the first, so on and so forth. Each trial happens in a vacuum. Again, we are imposing a statistical model. This is supposed to resemble reality. This is supposed to pick out the signal of reality. This is not supposed to be exactly reality. There are few processes, unless you're generating data using a computer, that are going to a T, follow any given distribution. But it is nevertheless going to be useful. So when we say this, there's several other assumptions that we are making. First of all, because it's a named distribution, we know the equation. So here is the distribution equation, and of the binomial. And what it shows us is actually the probability that my variable is equal to a given exact value. All right. So I'm going to color code. My parameters are going to be green. So here is n factorial. So to remember a little bit, right? This exclamation point is n factorial divided by x factorial. Yeah, put this on the outside. And minus x factorial. If this looks complicated, for the particularly complicated cases, we're going to use software. For easy cases, I will show you that there are a lot of special rules of how to compute factorials. All right, the factorial of 3 factorial is 3 times 2 times 1, for example. 4 factorial is 4 times 3 times 2 times 1. 0 factorial, and this is something we're going to use, is 1. So that's some factoids about the factorial that we have to remember a little bit about. All right. Then there is a multiplication sign. We have the probability of success raised to something. And we have the probability of failure, right? This is the probability of success. It's the same P. 1 minus the probability of success is then the probability of failure. And then these are raised to a power. So this is the probability of success raised to the number of successes. Here, 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 and here. And this is the probability of failure raised to the number of failures. So I'm saying it like this so that the equation makes just maybe a tiny bit of sense. The probability that my variable takes on any particular value, we have this multiplier, which is a ratio of factorials, right? This is the total number of trials factorial. This is the number of successes factorial. This is the number of failures factorial. And now we are multiplying two more terms together. The probability of success raised to the number of successes, and the probability of failure raised to the number of failures. The only reason we're able to write this out is because it's a named distribution and we have made these assumptions. And we can live with the assumptions. For a variable that has a binomial distribution, the mean is known. And it is just n times p. And the variance is known. Remember, the variance is just the standard deviation squared. And this is n times p times 1 minus p. So if you're trying to take the standard deviation, you just take the square root of the entire quantity, you get back to the standard deviation. These are known facts about the binomial. Okay, let's go through an example. Let's go through an example. So we're thinking of something where we want to model some number of successes out of some number of trials. All right. Suppose we have 5 patients in the ICU. The probability of survival for each patient is 0.8, 80%. I don't know if that's high or low. Maybe it's on the lowish side. I know University of Virginia is a very good hospital, but they're maybe in bad condition. Their probability of survival for these 5 patients is 80%. Okay, so with this kind of word problem, we're saying that, well, if we assume the patients are independent, or patient survival is independent, let's be more specific. Then we can represent this process using a binomial distribution. Number of patients that survive All right, and I'm going to do my tilde, which is distributed as a binomial distribution. And remember, I get 2 parameters inside the binomial distribution. This first one is n, right? My n is 5. And the second one is the probability of success on each trial, which is 0.8. Okay. So this automatically gives me a whole lot of information. For example, this is 0.8. Let's make sure that comes through. On average, 5 times 0.8, which is 4, right? 5 times 0.8, 80% of 5 is 4 patients will survive. Right, because this is simply applying the formula for the average, n times p. That's not that crazy, okay? If I have 5 patients and 80% survive, then on average, 4 patients will survive. Cool, nothing controversial here. So let's practice taking some more interesting probabilities. What if I'm somebody that likes a perfect record? What is the probability that all 5 patients survive? What is the probability that all 5 patients survive? The other way to read this is probability that exactly 5 patients survive. So this is my variable. Call this x, right? Is equal to 5 exactly. All right, and now I'm going to remember my equations for the binomial. N factorial, x factorial, n minus x factorial, total number of trials, number of successes, number of failures, probability of success raised to the number of successes, probability of failure raised to the number of failures. And this is telling me the probability that my variable takes on some exact number x. All right, my x is 5. Okay, but I know my n as well. I have 5 patients. I'm interested in all 5 of them surviving. And I know the probability of survival for each patient. That's 0.8. Notice here's the probability of dying. It's 0.2. Okay, so let's break it out. This multiplier, 5 factorial over 5 factorial. This is 0 factorial. Remember the special trick? 0 factorial is actually 1. That's the special trick. 5 factorial over 5 factorial just cancels out. And so this entire term goes away. Cool. 0.8 to the 5th power, probability of success on each trial raised to the power of how many successes I'm looking for. All 5 patients survive. Here is the probability of dying raised to the 0 power. And we'll just have to remember that anything raised to the power of 0 is also equal to 1. Anything raised to the power of 0 is equal to 1. So what I'm left with is 0.8 to the 5th power. And that computes out to 0.328. About 33%. So when you have 5 patients and your probability of survival for each patient is 80%, so the other way to say that is on average, 4 patients survive. The chances that all 5 survive are about 1 in 3. A little bit less than 1 in 3, 32%. See, I just applied the binomial equation because all 5 patients survive is the same as asking the probability that my variable takes on 5 exactly. Let's get a little bit more interesting. you can see how the question could have been exactly 4, exactly 3, exactly 2, exactly 1. That gets boring pretty quickly because you will have the binomial equation in front of you. You just plug in the numbers and there goes the answer. What if you're looking for the probability at least one patient survives? If before we were setting a high bar, we want to be 5 for 5. Here, we're setting quite a low bar. We're saying, hey, man, I just need at least one of these guys to pull through. At least one patient survives. At least one. Okay, so we have to do some rewriting. This is the same as the probability of 1 or more. All right, and now we've got to remember unions. This is the same as, okay, so when I have 5 patients, my sample space, remember sample space? List of all possible outcomes. I can have no patients out of 5 survive. I can have 1, I can have 2, 3, 4, 5, the end. So look, this is a bounded sample space. I cannot have less than 0 patients survive. And I also cannot have more than 5 survive out of 5. So for my little bit more interesting query about probability of at least one patient survives, so this is the same as the probability of 1 or more. So probability that my variable is equal to 1, union 2, union 3, union 4, union x equals 5. A union of 1, 2, 3, 4, 5 different events. Cool. I better get to it evaluating 5 binomial distributions, or not. There's only one event in the sample space that is excluded from at least one patient. That is the probability of 0. So I can go ahead and just rewrite this as the probability of x equals 0 complement. And now I don't have to evaluate 5 different probabilities. I just need to evaluate 1 because we know the rule. This is 1 minus the probability of exactly 0 survivors. I just need this one probability, and then I'm going to subtract it from 1. So one minus probability of exactly 0. All right, so 1 minus n factorial, successes factorial, failures factorial, probability of success raised to the number of successes, probability of failure raised to the number of failures. A little bit quicker, I have a sample size of 5, n equals 5. I'm looking for 0 successes out of 5. My probability of success is 80%, and I'm looking for 0 successes. My probability of success is 80%, and I'm looking for 5 minus 0 failures. So when I break this down, 0 factorial is 1, and this is 5 factorial over 5 factorial. This entire thing goes to 1. 1 minus 0.8 to the power of 0, 0.2 to the power of 5. 0.8 to the power of 0 also goes to 1. And what I'm left with is 1 minus 0.2 to the power of 5. 1 minus 0.2 to the power of 5, you should recognize that 0.2 to the power of 5, right? 0.2 times 0.2 times 0.2 times 0.2 times 0.2, I think that's 5, is a very small number. So this is 0.99, one more 9, 7. So whereas the probability, if with this setup, I have 5 patients, the chances of survival are 80% per patient. The chances of all 5 surviving was only 1 out of 3. Those are not great chances. At least one, I am nearly certain that at least one of these guys is going to pull through. At least one is almost certain to pull through. Now, you can apply the same idea if I said, all right, probability of at least 2, right? Okay, probability of at least 2, you got to transform this into 2 or more. And now you're going to decide, well, I don't want to compute the probability of exactly 2 or exactly 3 or exactly 4 or exactly 5. The only 2 that are excluded is 0 and 1. Right? So then what I can do, 1 minus the probability of exactly 0 or probability of exactly 1. Now remember that or means we add probabilities together. And so you're just going to make sure to do your order of operations right. You're going to add things up first, then subtract them from 1. Okay? Okay. Let's look at, all right, we defined random variables. We are moving right along here, and we just talked about the binomial. Let's look at a different distribution. So the binomial is used for counts. It's to model some count out of some known n, some known number of trials. The next distribution also models counts, but a little bit different. And it is called the Poisson distribution. For the French speakers, Poisson, right? Whoop, let's see. Poisson, fish. This is some number of, I'm going to call it successes. We can call it events. Some number of events per unit of space and or time. Notice nowhere in here there isn't some number of trials, no n. But it is still a count. All right. We have a distribution equation. Probability that my variable takes on a particular value. And I think it's a good idea that I actually color code this. All right. So sorry, I'm getting ahead of myself. We say that our variable is distributed according to a Poisson, where the parameter is lambda, right? Here is my variable. This is distributed to This is a different name distribution. It's not binomial anymore. It is Poisson. And this is the only parameter. The Poisson depends on just one parameter. It's usually lambda. And this defines the shape, the mean, and the standard deviation. All three things. So the distribution equation looks like this. E to the negative lambda, E taken to the power of negative lambda, lambda to the x, divided by color coding x factorial. E to the negative lambda, lambda to the power of x, divided by x factorial. This is the probability that my random variable takes on a particular value of x. The assumptions that we're making, all events are independent. So that's a big one, right? You can think of this being the number of COVID cases per county per day. The number of COVID cases per county per day. All of the COVID cases are independent? I don't think so, right? Infectious diseases really violate this assumption. So I have to be very careful with my example. And the average is equal to the variance. So this last one is a bit technical, but it is not uncommon for the variance. Again, the variance is just the standard deviation squared. It is not uncommon for the variance to often be bigger than the average, but this distribution very much assumes that the mean is equal to lambda and the variance is equal to lambda. And again, just because we haven't talked about the variance much, this is just the standard deviation squared. So the standard deviation is the square root of lambda. So these are the assumptions imposed in whatever process you're trying to model if you assume your data follows the Poisson distribution. But when you assume that your data follow the Poisson distribution, you can find the probability that your variable takes on any given value. So the example, and I'll go through it a little bit faster because this is going to be very similar to the binomial, just the equation is going to be different. All right, for example, there are 1.5 Alzheimer's deaths per year in Charlottesville. It is now fair to assume that all of these events are independent. Well, this next assumption might be testable, might be not, but I think that they're dying of something that is not immediately infectious. And so notice that there's also no sample size, right? There's no sample size anywhere. No sample size. We don't know how many patients we had, but we know that on average, there are 1.5 Alzheimer's deaths per year in Charlottesville, right? Per unit of space and or time. And here I have space and time. All right. I can compute their, for example, probability of having exactly no deaths. Yeah, I'm just going to plug it in. E to the negative lambda, lambda to the 0 factorial. And I just need to plug in my value of lambda. And by the way, I am assuming that my variable follows the Poisson distribution with lambda equals to 1.5. So now here is my probability, right? This is lambda, e to the negative lambda, lambda to the 0 factorial. We know that 0 factorial is 1. We know that anything to the power of 0 is 1. So this is e to the negative 1.5, which is the same as 1 over e to the power of 1.5. And this computes out to 0.223, about 22%, about 1 out of 5. So if I have 1.5 Alzheimer's death per year in Charlottesville, the chances that we'll have a year in the city with no deaths at all, even though the average is 1.5. The average is 1.5. The probability that I will have exactly 0 deaths, it's a good year, 22%, or about 1.5. So intuitively, what happens if my rate increases? If my rate increases, what do we expect to happen to the probability of no deaths at all? All right, so suppose instead of 1.5 deaths, I now have 3 Alzheimer's deaths per year. Okay. I just changed the average of my distribution, right? The mean is now 3 deaths per year in the city of Charlottesville. I can still compute the probability of exactly 0. And this computes out to e to the negative 3, 1 over e to the 3rd. And this is actually 0.0498, or about 5%. So look, my average doubled, but the probability of having no deaths dropped by about 4-fold. Right? This is approximately 5%. Before it was 22%. And then everything that we talked about with the binomial applies. At least 1 death, at least 2 deaths, at most 1, at most 2, not 0, so on and so forth. Okay? The equation is different, but the logic about at least 1 being 1 or more, at least 2 being 2 or more. By the way, the sample space, 0 is in the sample space. We just computed the probability for it, for a Poisson, 1, 2, but it is now unbounded. The sample space is unbounded. If you remember the binomial, the sample space was bounded by n. You can only have up to n successes out of n trials. All right, so to close out today, we're going to look at the distribution that you might be familiar with, and it's the normal distribution. And we're just going to get started on it today. All right. Normal distribution. So when I say something has the normal distribution, right, you're thinking bell curve. You're thinking a sample space that is all real numbers between negative infinity and infinity. So if the binomial was a bounded sample space, the Poisson was bounded only below by 0. The normal is all real numbers between negative infinity and infinity. We say that our generic variable is distributed according to the normal distribution. And the normal distribution, n for normal, tilde distributed as, has two parameters. The mean and the standard deviation. The first space here is going to be the mean, and the second one is going to be the standard deviation. The notation, remember, for the binomial was NP. For the Poisson, it was lambda. For the normal, it's mean mu, and a standard deviation sigma. In some cases, you will see this in terms of the variance, but because the standard deviation is more interpretable, I write it in terms of standard deviation. If you look at it in terms of the variance, again, you just square the standard deviation, you get the variance. So this means that the mean of x is mu, and the standard deviation of x is sigma. So this is a recurring theme, isn't it? That these parameters are nicely interpretable, right? For the binomial, n times p was the mean. For the Poisson, lambda was the mean. For the normal, it's whatever this parameter is, that's the mean, right? But because it's a normal distribution, this is also the median and also the mode, right? Super interpretable if you make the assumption that something is distributed according to a normal distribution. All right, let's draw the normal distribution. Of course, I'm not going to draw a line between negative infinity and infinity. We're going to zoom in a little bit. Here is my generic variable x. And I have a bell curve. It is going to be centered at mu. All right, how do we show the standard deviation? Well, the interpretation of the standard deviation is that it's the average distance of the data to the mean. But it kind of has a couple of anchor points, if you will. So around halfway here, you can see that the curvature changes. As we go up here, this line curves up, and then it curves down. Curves down, curves up. So this curvature changes, actually, right at a known point. And that's if we add a standard deviation to the mean, or, you know what, I have that backwards. We add a standard deviation to the mean, we subtract the standard deviation from the mean. That is the point where that curvature changes. And we can keep going. This point is about 2 standard deviations from the mean. This point is about 2 standard deviations from the mean in this direction. So when we say something follows a normal distribution, we're imposing sort of a sliding bell curve. And when we increase the mean, for example, right, we're going to slide the entire thing over in this direction. Right? The entire thing is just going to shift in this direction. If we decrease the mean, well, It's going to shift in this direction. If I leave the mean alone and I decrease the variance, that might be a little bit harder to imagine. So let me draw. Okay, I'm going to decrease the variance, but I'm going to leave the mean alone. So if I decrease the variance, all right, got to color code correctly. Decrease the variance, I will have less variability, and so a higher peak. More data around the mean. Something like that. Smaller sigma, same mean mu. So you see, these are very powerful two parameters. We can make the distribution as wide or as narrow as we want, and then we can shift it around by changing the mean. This line has a formula. I don't care for you to memorize the formula, at least not in this class, but we will pick up the next class by learning more about the normal distribution and learning how to take probabilities in a normal distribution. The thing is that we now are dealing with a quantitative continuous variable. And this means that the probability that the variable, a quantitative continuous variable, is equal to an exact number is actually 0. Let that sit for a minute. Remember that you can always find a number between any two real numbers. We have a quantitative continuous variable. The probability of us hitting one of those values exactly is 0. So the only thing we can compute is actually probability in intervals. So here is my variable. Here is my normal distribution. Here is my mean. For example, here are two numbers A and B, and it is the area under the curve that is the probability that we are bigger than A and smaller than B. This is going to be not 0. Okay, so let me pause for today. We had plenty of new material for today. Next time, we'll pick up about a little bit more about the normal distribution and how to compute these probabilities without integration. All right, guys, thanks for your attention. Virtual class next. I will see you soon.